Okay, welcome to the public exposition of the master thesis of Miguel Ángel González Casado, what coevolution and coordination means.
Okay. To begin with, the question we want to answer in this thesis is the question about how people can self-organize and form groups. Basically, we want to understand the process of this spontaneous emergence of coordination without an external enforcing. But first, we need to understand what coordination is. Coordination for us can be defined as the choice of the same action by all the members within a group. And it is important to notice that the fact that they all choose the same action is beneficial for them. For example, you can imagine an IT company where all the colleagues need to use the same programming language. If they all choose the same programming language, they are good. So this is an example of coordination. A more sophisticated example of coordination is mass mobilizations. In mass mobilizations, people have two possibilities. Either they can join the mobilization or they can stay aside. If they stay aside, the status quo remains unchanged, but at least anyone is harmed. But if everyone joins the mobilization, most likely the mobilization will succeed. So the key point is that every possibility is good as long as everyone else chooses it. This is the idea behind coordination. And to study these kind of situations, we use the framework of evolutionary game theory. Specifically, we are going to focus on a specific type of games that are called coordination games, in which we study this competition between strategies. But apart from coordination games, we need to take into account that the model may be too simple if we only consider competition between strategies. We need to take into account that real world communities evolve in time. And to take that into account, we introduce the concept of coevolution. Coevolution refers to the time evolution of every characteristic of the system that is not the competition between strategies. We will develop that later. And in this thesis, we precisely do this. We study the interplay between two mechanisms, the competition between strategies and the evolution of the network. And in this framework, we want to understand first, under which conditions can coordination in a single group or segregation in different groups can emerge. And if there is coordination, we want to understand which strategy is selected. But first, we need to introduce coordination games. Basically, in coordination games, we have two agents and they are forced to interact. And in this interaction, they can use two possible actions, action A or action B. And they receive a larger payoff if they both choose the same action. Within coordination games, we can have two types of coordination games, pure coordination games and general coordination games. In pure coordination games, agents receive the larger payoff if they coordinate on the same action. And they don't receive payoff if they don't coordinate in the same action. So we can say that both strategies are equivalent. Then in general coordination games, we have different situations. Both actions are no longer equivalent. And here we have that if this payoff matrix in which we impose these two constraints. So what happens is that coordination on action A yields the highest payoff. It means that action A is the most profitable strategy if we reach coordination in this strategy. So that is why we say that action A is the payoff dominant strategy. However, in coordination games, we can also introduce the concept of risk. Imagine you are player one and you choose strategy A. If the other player also chooses strategy A, you receive the largest payoff possible. But if the other player chooses strategy B, you lose S. You earn S, but S is negative. So basically, you are risking by choosing strategy A that the other agent doesn't coordinate with you. This also happens for the other strategy depending on the value of T. And this is better understood if we plot the parameters space. This figure is taken from this paper. Here, what we can see is that this line separates the parameter space in two regions. The region above, in this region above, the safer strategy is strategy B. And this is why we say that strategy B is the risk dominant strategy. And below this line, the safer strategy is strategy A. And this is why we call this strategy a risk dominant strategy. And in the whole parameter space, action A is the payoff dominant strategy. Now we know how these strategies are, and we need to know how they are going to evolve in time. And to do so, we are going to introduce at each time step, we are going to select one agent within the network after this agent have played the game with all its neighbors. And we are going to compute these payoffs of each of the individual games played. And we are going to consider that the payoff represents the average reproductive success of this player, so that this player, for example, is more probable that his probability is going to reproduce than the strategy in this other player. And to implement this within an algorithm, what we need to do is to use the so-called selection rules. Here we are going to focus on two selection rules, the replicator dynamics rule and the unconditional limitation rule. In the replicator dynamics rule, we consider, imagine that we focus on agent A, and we choose randomly one of the neighbors, for example, this other neighbor. Since the other neighbor has a larger payoff, we are going to consider that with a certain probability, our agent is going to copy the strategy of the other agent. And the probability of our agent copying is going to be larger if the payoff difference between both is larger. So we could end up in two situations: a situation in which our agent copies, or in a situation in which our agent doesn't copy. In the unconditional limitation rule, the situation is different. In this case, if we focus on agent A, this agent always imitates the neighbor with the largest payoff. So in this case, since this is the neighbor with the largest payoff, there is only one probability of him not changing strategy. Now we want to add coevolution. But what is coevolution in the first place? I said that it represents the time evolution of every characteristic of the system apart from the competition between strategies. For example, it could refer to the growth of the network, to the mobility of the systems, or to the change in the connection between agents. And we are going to focus on this last part. Basically, if we focus on agent A again, and this agent is connected with an agent using the opposite strategy, we are going to give our agent the possibility of putting the link with an agent in the opposite strategy and reconnecting this link with a random chosen neighbor. And we are going to let this happen while the competition between strategies occur with a certain probability that we are going to call requiring probability P. So depending on the value of the probability P, we are going to have different outcomes. For example, let's focus on the first case. We are going to focus on the case P equal to 0, when there is no coevolution, only competition between strategies. And in this case, the situation is simple. There is a competition between strategy, fast competition, and we end up in a situation in which the system is fully coordinated on one of the strategies. If we consider only coevolution, what happens basically is that only links cut and are reconnected to other neighbors, so that the system fragments in two pieces, one of them connected in one of the strategies. And we can have an intermediate situation. For example, let's consider this one. For intermediate values of P, we could have, again, coordination in a single component, fragmentation into components, or we could have different outcomes like this one. For example, we are going to have coordination in a single connected component, isolated nodes, a small component, also another connected component. And this is precisely what we want to study here. So to begin with, we are going to focus on the case of pure coordination games in Erdős-Rényi network. And as the starting point, we're going to reproduce these two plots from this paper here. And in these two plots, what we are going to do is to set the system, an Erdős-Rényi network of 1,000 nodes, and we are going to let the system evolve using the rules I've explained. And when the system reaches a frozen state, we are going to measure first the fraction of agents that are on action A, which we are going to call alpha. Second, the density of active, and second, the density of active links, that are the links connecting nodes with using different strategies. And we are going to measure these two quantities as a function of the mean degree of the network. In this case, in the plots, you see the average density of active links in the frozen state in a red line, and you are also going to see the specific results for realizations for alpha in green points, and in black, the average value of this alpha. And what we observe, also here, I represent the proportion of realizations that end up in a single connected component coordinated. And here we see that for the replicator dynamics, for values of K above 10, the system fully coordinates on a single strategy, either on A, if the value of alpha is 1, or on B, if the value of alpha is 0, and the density of active links is 0. However, in the case of the unconditional limitation, the situation is quite different. We can also have realizations in which the system fully coordinates. And in fact, for example, if we focus on k equals 30, the proportion of realizations that end up in full coordination is 79%, more or less. But we could also have realizations in which the system freezes in a value of alpha, which is not 0 nor 1. So we want to study in these two pictures what happens if we add coevolution. First, we want to know, for this first case, we are going to focus on k equal to 30. And for the replicator dynamics case, we want to know if coevolution fragments the system. And for the case of the unconditional limitation, we also want to know if coevolution fragments the system, but also we want to know if coevolution is able to reactivate frozen states, frozen configurations, and enhance full coordination of the network. For the first case, for the replicator dynamics case, in k equals 30, what we are going to do is to, as a function of the regarding probability p, we are going to measure alpha, the proportion of realizations ending in full coordination, but also we are going to measure the number of fragments and the size of these fragments of connected components. Basically, here what we see is that for low values of alpha, for low values of p, the system again coordinates in a single connected component. But as we increase the value of the regarding probability, we reach a regime in which the system is able to coordinate to fragment in two connected components, each of the components coordinated in one of the two strategies. So we can see that there is a what we are going to call a fragmentation transition from a regime in which the system fully coordinates on a single component to a regime in which the system fragments in two components, each one coordinated in one of these strategies. For the unconditional limitation case, the case is quite different. We had frozen states, and now for low values of the regarding probability, we see the black line is the proportion of realizations ending in full coordination without coevolution, and in purple with coevolution. And we see that the proportion is more or less similar. So it seems that coevolution, that realizations that already coordinated in the case without coevolution still coordinate, and the rest of the realizations simply break into pieces. This is why we have these points in two here. This is an example of this case, this fragmentation. Then for large values of p, we have two fragments, each one coordinated on one of the strategies. And for the difference here is that for intermediate values, what we have is a multiple fragmentation. There are no longer two fragments, but there are multiple fragments up to 20 fragments. So it seems that instead of having this clear transition, we have an intermediate regime with a multiple fragmentation. We have examples here. First, when we increase the regarding probability, we reach a regime in which we have a large connected component and small pieces around. And if we continue increasing, we reach a regime in which we have a large connected component, a small connected component, but also large, and isolated pieces. And if we continue increasing, we reach the regime of just two pieces. This answers the question about if there is a fragmentation transition, but we have not answered fully the question of if does coevolution help reactivate frozen state to reach full coordination. And it seems that the proportion is similar, but if we look closer, what happens is that points with coevolution are above points without coevolution, meaning that the system is able to, that coevolution is able to reactivate some frozen state, helping the system reach full coordination, but this improvement is marginal. This is a summary of these two results. Here we present for both rules the standard deviation of the PDF of the three distributions. And here we can see that for the replicator dynamics, there is a single peak for the three distributions representing this clear transition from the regime of full coordination to the regime of fragmentation. For the unconditional limitation, we have more like a crossover in which there is this intermediate regime with multiple fragmentation, and this is why there is a succession of peaks in the different distributions. We have produced other results, like we have studied the role of K and the case for low K, and you can ask me later if you are interested, but I prefer not to focus on this one, just to have time to describe the rest of the results. Now, for the case of a general coordination game in an Erdős-Rényi network, I recall that we had this black line, which was the transition line between the region in which strategy B is the risk dominant strategy and the region in which strategy A is the risk dominant strategy. And again, as the starting point, we are going to reproduce the results present in this paper. here what we measure is for each pair ST in the parameter space, we're going to measure on which strategy the system coordinates. Green represents coordination on A and yellow represents coordination on B. And what happens for the replicator dynamics case is that the system always coordinates on the risk dominant strategy. And that is why the transition line is coincident with the black line. In the unconditional limitation case, the case is different. Here we have both lines are not coincident. So we have an intermediate regime in which the system is able to coordinate on the payoff dominant strategy, even if this strategy is not the risk dominant strategy. Now we want to add coevolution to this picture and see how it changes. We are going to focus only on the replicator dynamics case because the unconditional limitation case is analogous, the results are analogous, and I have them at the end if you want to see them, but I think it's clearer if I only present the replicator dynamics case. And we want to add coevolution, and we want to answer 3 questions. First, is there a fragmentation transition like in the case of pure coordination games? Second, if there is this fragmentation transition, does one of the components coordinate on the payoff dominant action? Because I recall that here coordination was always on the risk dominant action. And third, we want to know if the system is able to fully coordinate on the payoff dominant action. And to answer to the first 2 questions, we are going to focus on these 3 points of the parameters space. These 3 points correspond to these 3 columns here. And basically, we are going to follow the same methodology. We are going to, as a function of P, to measure these 3 quantities. And we observe that the result is analogous to the case of pure coordination games because for low values of the regression probability, we have that the system does the same it did without coevolution. And for large values, we have a fragmentation transition in 2 pieces with one of the strategies coordinated in one of the components coordinated in each one of the strategies. This answers the first 2 questions. There is a fragmentation transition analogous to the payoff to the pure coordination game case. And this fragmentation transition allows the system, a part of the system, to coordinate on the payoff dominant action. However, there is a more interesting result hidden here. And if you concentrate here, you see that the points are chosen symmetrically with respect to the transition line. But here results are not symmetrical. Here we have like a straight transition, and here we have like a more curved transition. And the point chosen right at the transition is not symmetrical. It's clearly balanced towards the strategy A. So to understand what's happening here, what we did was to measure the same quantities, but in a point closer to the transition line. And in this point, what we obtain is this. Surprisingly, a second transition appears before the fragmentation transition. At first, the system coordinates as before in the risk dominant strategy, but we can cross a value of the regression probability in which the system fully coordinates on the payoff dominant strategy, even if this strategy is not the risk dominant strategy. And then obviously we have the fragmentation transition. So it seems that in this picture, the transition line is displacing with respect to the black line towards the region in which strategy B is the risk dominant strategy. And to see if this is the case, what we did was to compute this phase diagram, but for different values of the regression probability. Here we have increasing values of the regression probability, and here we have the summary of the transition lines. And it is clear to see that as we increase the regression probability, the line displaces towards the region in which strategy B is the risk dominant strategy, enable the system to fully coordinate on the payoff dominant strategy. Just to complete the picture, what we wanted to know is the value of the rewiring at which this first transition occurs, at which the system is able to fully coordinate on the payoff dominant strategy before the fragmentation transition. And this is why we only focus on this red line here, fixing the value of t, because outside we have only fragmentation transition. And here we measure this value needed for the system to fully coordinate on the payoff dominant strategy. And as we approach the transition line, sorry, the value of the rewiring needed to fully coordinate on the payoff dominant strategy lowers. This result was expected because the closer we get to the transition line, the easier for the system it is to coordinate on the payoff dominant strategy, because both strategies are more similar. Just finally, to conclude, what we have seen is that coevolution leads to a fragmentation transition, both in pure coordination games and in general coordination games. And this transition has a different nature depending on the selection rule we use. Also, from this, we can conclude that coevolution promotes coordination in segregated groups, because if the system fragments, we have each group coordinated on one of the strategies, so there is coordination, but within segregated groups. And we have also seen that for these cases in which there were frozen states, the system slightly stimulates coordination in a single connected component, but this improvement is marginal. And the most interesting result is that coevolution enables the system to fully coordinate on the more profitable strategy, even if this strategy is the riskier strategy. Finally, as a final remark, future work should be focused first on developing an analytical model to at least predict this fragmentation transition. And also, we will have to look for support with experimental studies in real human networks, and also on implementation of more realistic rules. For example, beyond replicator dynamics and unconditional limitation, focus, for example, on rules like the reinforcement learning rule. And thank you for listening.